Most vectors are free. There's like, in mathematics, the most free society of math. Vectors are free. If you have a column vector like 2, 3, it could start anywhere. And wherever it starts, it goes to the right and 3 up, and that's where it ends. Start anywhere, end anywhere. That would be a free vector. Now, sometimes we want to do math where we fix something in place. Then we use a position vector. And as a position vector, 2, 3 is the same as the point 2, 3. Because a position vector always starts at the origin and goes to some point. So here we have the point x, y, and we call it the position vector p, because you go from O to P. And this is going to be helpful for us figuring out some mathematics. So we're going to sketch the position vector passing through the point -6, 5. So there, we find the point -6, 5, draw our vector from O to P. Then we could write this vector with our component vectors, our unit vector I and unit vector j. Or we could write it as a column vector, which, I don't know about you, but I like a lot better. So you can always write, if you go through a point, its position vector is always the x-coordinate and the y-coordinate, and you can write it either as a column vector, or you could write it with the unit vectors I and j. Not super hard. Now we're going to consider the points 1, 3, and 4, 5. And we can draw their position vectors. The blue one is the position vector for A, and the green one is the position vector for B. And this is where I think vectors start to get fun, when we start to do some math with vectors. Because every point has a position vector. It's really easy to find the position vector of any point on the graph, because you just have to have the x-coordinate and the y-coordinate. But let's say we want to find the resultant vector. The resultant vector is saying, I want to go from A to B. If I was at A and I wanted to go to B, what would the resultant, what would that vector be? And this is where vectors are interesting too, because they're not really concerned how you get there. You just need to get there, right? You're supposed to get to school in the morning. I don't care what road you take. I just care that you get here on time. But you can choose all sorts of different roads to get to school. So if you're at A and you want to get to B, you could always decide first to go to the origin and then to go to B to get there. But if I'm at A and I go back to the origin, does it make sense that A to the origin is just the negative? Because the same vector in the opposite direction is just the negative of that vector. So on the graph, AB is 3, 2. But I could also say that AB would be the same as starting at A and going to the origin, and then going from the origin and going to B. A to the origin, well, the vector A is 1, 3. That's my position vector. That's OA. So AO would be negative 1, 3, because it's the same vector in the opposite direction. And then OB was 4, 5. You see the math? And negative 1 plus 4 equals the 3. The negative 3 plus the 5 equals the 2. So if I give you any 2 points and say, how would I go from one to the other, you can use this mathematics to figure it out. Now, I will often write it like this. I said, I'm starting at A, I'm going to go back to my origin, and then I'm going to go from my origin and go to B, because that makes sense to me. Mathematically, they often write it as the flip, because they like to have the subtracting second, right? Because this is really negative A plus B. So they're like, well, why don't I just write that as B minus A? It's the same thing. So you'll often see B minus A, but I actually, personally, I still like writing the negative A plus B because it's really easy for me to visualize. If I want to get from A to B, I could go back to the origin, which would be negative A, right? This one here is negative A. And then once I'm in at the origin, I could go positive B to get to B. So as a visual, I like this formula as negative A plus B. I understand as a formula, it's awkward to start a formula with a negative, so let's make it B minus A as a formula. But many questions, if you want to visualize them, they're going to be easier if you just write it out exactly as you visualize it. Okay? What would happen if you did B minus A? If you did B, that means you're starting at the origin. You would go to B, and then minus A would be down to here. You would get there, and then this would be the resultant. It's in a different place, but vectors are free. As long as it has the same length and the same direction, it's the same. It doesn't matter where it starts. Only position vectors are forced to be in their spots. But the vector AB, which is 3, 2, could be anywhere. And this is what makes math with vectors quite powerful, because you're not restricted to stay in certain spots. You can figure things out by moving around and not being worried about it. Then again, I'm going to write this out. It's easier to visualize negative A plus B. But it's a nicer formula when it's written as B minus A. Now we're in 3 dimensions. And you're at some point A and you want to get to some point B. And someone says, what direction and how far should I go? Well, in 3 dimensions, again, we're imagining somewhere there's a vector A, somewhere there's a vector B. We can imagine those arrows in 3 dimensions. And you want to figure out A to B. If I'm starting here and want to end there, and I'm only allowed to travel along blue paths, I would first go back this way, which would be negative A. And then I would go this way, which would be positive B. And of course, that's equal to B minus A. So if we write it as B minus A, you'd have vector B minus vector A. And it's saying that you would need, if you were at A and wanted to get to B, you should travel 6 in the x direction, minus 10 in the y direction, and minus 3 in the z direction. And you could do BA in the same way. Say if I'm starting at B, I would go negative B first, and then I would go be a positive A. But I might also just say that if I know AB, then BA will just be the negative of AB. And it doesn't have to be origin vectors that you know. You could know other vectors from different places. So if I'm at Q, here I'll put it in green. This is my starting point, and I want to end at R. But I'm only allowed to travel via the other paths. And this is why I think doing the negative makes sense to do first. Because doing the negative first says first you would go, I'll do it in purple, first I would go negative PQ, which is the same as going from Q to P. And then I would go plus PR. And negative PQ plus QPR would get me from Q to P. When we write it like this, I'm going to erase this color temporarily, and then I'm going to nicely draw P to R in green. Oh, that's a beautiful looking vector. And I'm going to nicely draw P to Q, but negative P to Q would be this way. And when I write it like this, it's saying Q to R is like going P to R first. Well, I'm starting at Q and I'm going P to R first. I'm going to move that. Since vectors are free, I'm going to move it up there, because that's what I'm doing first. And then I'm subtracting P to Q, and move that second. Notice I get to R. But it's not as easy to visualize because those lines weren't drawn there. But since vectors are free, you can travel in those directions at any time. Okay? I find it easier to visualize using the lines that are already there. I would have done the blue first and then the green. So doing the blue first, that would be Q to P, which is negative PQ. I would have done that first. And then I would have added P to R. Because that is following the lines that they gave me. And as your brain works, that's easier for you to do. It's not as easy for you to see, oh, I'm going to go off in space this way, and then I'm going to come back and make a parallelogram with the ones that I drew. But it'll still get me to the same spot. So given xy is 543 and xz, oh, I have to undo that one, is 1002, could you go from y to z? So one thing that's similar to matrices, you know how matrices, when you multiplied, you needed those middle numbers to match up? When you write out an equation, which I'm going to put in the blue box right here, does y to z make sense? If you first went to x and then went from x to z, you would get from y to z. If those middle letters are the same, that's just like going from y to z. Right? So because this x and this x are the same, really I can combine those two together and say that's y to z. But I don't know, when I look at what I was given this. I was given x to z, but I wasn't given y to x. But I can make y to x negative and flip it. Because going from y to x is the same as going to the negative x to y. And negative xy is just our first one with the negative plus our second one. Again, here's a picture. Just draw 3 dots. Make one x, one y, one z. And pretend you're in 3 dimensions. And you're like, I'm an excellent drawer. Right? If I want to go from y to z, I think it's easiest to visualize first going negative xy, and then going positive xz. So you can either draw the diagram to get what you want to do, or what we did in the equation is we broke up y to z by making a stopping point in between. Right? Sometimes it's too long to drive all the way home, and you have to have a stop at McDonald's or at Starbucks on the way. So now, from here to home, school to home, now has school to Starbucks to home. You still get home. You just had a stopping spot on the way. Same thing, y to z. Now if we think of the diagram, if I want to go from y to z, here's the formula, but I would think of the negative y first, and then the negative z after. And there's the end. And this is the starting of vector math. Vector math says, hey, we can add vectors together, we can put things, directions together, and figure them out. And almost always we'll be working in 3-dimensional spaces, because that is where vectors are most powerful. Plus, in 2 dimensions, you've already done equations of lines, and you're pretty good at it. So it doesn't really make sense to invent something new for something you're already good at. But in 3 dimensions, you're not good at working with, and vectors work really nice. So here are 3 vectors, A, B, and C. So one vector goes like this, another vector goes like this, another vector goes like this, and they want you to show that all 3 of them, oh, that's pretty good, line up for a straight line. They're all collinear, meaning that if you joined all those 3 vectors up, all those 3 points, they would be in a straight line. So here's the idea. A, B, and C are all in a straight line in 3 dimensions. How could we show that? We can't just show that AB plus BC equals AC. Because in vectors, if you go from A to B and B to C, you'll get to A to C. That doesn't necessarily mean they're in a straight line, right? So how do we think and how do we show that they are in a straight line? Well, we could figure out what A to B is. That's my vector from A to B. It's just going to be B minus A. That's using the formula. Same thing as thinking, I could think of it as negative A would get me back to the origin, and then going to B would get me to B. That's using a visual, or you could use the formula. Same thing, you could find from B to C. If they're on a straight line, does it make sense that A to B and B to C have to be parallel? Have to be the same slope. How do you show if 2 things are parallel? If one is a multiple of the other. And as you can see right now, if I times AB by 3, I get BC. Then we know they're parallel. And since they share a point, right, if you have one parallel vector and another parallel vector, and they have the same point in the middle, they must lie on the same line. I think this is the shortest way to show that these three are parallel. Another method you could do is you could find the magnitude of A to B, right, by doing the square root of 1 squared plus 3 squared plus 2 squared. You could find the magnitude of B to C by doing the square root of 3 squared plus 9 squared plus 6 squared. And you could find the vector A to C and find its magnitude. And if the magnitude from A to B plus the magnitude from B to C equals the magnitude from A to C, they have to be in a straight line. Because if they're not on a straight line, can you see that A to B and B to C is longer than A to C? That one would be longer. So it'd be like, this takes me longer than just going straight line. But if it's exactly the same length, then you were traveling along a straight line all the way through. All right, one for you to try. Can you find the vector from A to B? And then find the distance between A and B. Did you get from A to B was -1, -410? And the distance, just square each of them and put in a square root. Square root of 117. And now we get to some math of vectors. So we've basically done this math already. Does the visual for U and V make sense? Vector U says go 5 to the right and don't go up. Vector V says go 4 to the right and go 5 up. So here's the vector U, and there's the vector V. What does U plus V mean? Well, if I draw U in green, and I draw V in blue, this is what U plus V means. You do U first, and then you do V. So when you're adding vectors, you can put them anywhere, because vectors are free, but you're going to put the tail of your second vector to the head of your first vector. Because if you did U first, this is where you got to, and then if you're going to do V after that, well, you're going to have to, from where you got, this is where you're going to end up. And this is what has happened. And that red one goes 9 to the right and 5 up. So somehow we have to figure out some sort of math, probably extremely complicated, to get this answer. Any suggestions? I like the look on your face. You see it, but the way I made it sound too complicated, so you don't know if you want to say it. Pretty straightforward, right? All you're doing is you're adding your x values and adding your y values and getting the answer. There it is. There's the resultant. And again, everything, we highlight something important here. You're matching things up head to tail. And it doesn't matter actually which way you do it, because if you added v plus u and u plus v, they would end up being the same. There is the answer. Adding the corresponding components. You don't need to write that. That's okay. You want to write the I and the J. All right. Well, if you can't not write what I have up here, there you go. Make sure that's in your notes. So 50 plus 45 will be 95. If u is 50 and v is 4, 5, u minus v means that you're going to go u first, and then you take v and go in the opposite direction, and you get subtraction. And once again, it's as easy as just subtracting the corresponding components. Now we could draw all of these out. Here's A plus B, drawn out. And if we draw out A, and we draw out B, happening tail, head to tail, and then we start at A and go to B, and count it out, you're going to go 1 to the right and 2 up. But you're going to find that you're not going to want to draw things out. You're instead going to say, well, I know that A is 2, -1, and I know that B is -1, 3. So it's really easy to see that A plus B is going to be 1, 2. But drawing it out shows you that it works as well. You have the B, and then you go -A, which is just the A in the opposite direction. Then you get B minus A. Again, you could do the components to figure this out. But drawing it does help show what it looks like. 2B would just be the B doubled. 2A would just be the A doubled. And then you count the resultant. Check. Did you get 1, -1, 7? 4, -1, and 5/2. And 12, -2, and -1. Which one? Oh, decimals is fine. You got 2.5?
No.
Within and not fine.
I have 5.5.
minus 1.5? So did you do 4 plus 1.5?
Yeah.
So that's probably what went wrong.
Yeah.
Now again, I really find for questions, it's really nice if you draw a vector diagram to help you visualize. You've got A to B. You know B to C. And you want to find A to C. Does it make sense that if you went from A to B and then from B to C, you would get from A to C eventually? Just would take you longer. Anthony wants to go to Charles' house. But on his way, he picks up Bob. So you can't go straight there.
Bob sounds like an inconvenience.
Bob is an inconvenience. Bob is the life of the party. You don't want to go to Charles' house without bringing Bob. So then we write out our columns and add them up. These diagrams are super easy to make, right? Make a point A, make a point B. Draw an arrow, that's vector AB. Then you're like, oh, I've already got a point B, I can make a point C anyway, right? This is C. What do I want to find? I want to find from A to C. How could I get from A to B if I only know the blue lines? Well, I go from A to B and then B to C. So you've got a really basic robot that can only travel in 2 directions. It can only travel in the direction from A to B, and it can only travel in the direction from B to C, but you need it to go from A to B. So you make it travel the routes that it can, so it can get to where it needs to go. Again, draw out our diagrams. There's A to B, there's A to C. We want to find B to C. So when I draw out my diagram, I can say that if I want to go from B to C, I can go from B to A and then A to C, because I'm only allowed to travel along red routes. B to A, of course, is the same as negative A to B. So now I have an idea, now I can put my math into equations. And of course, if you like, you could also think of the formula, although sometimes I find if you're just using a formula and you don't visualize what's happening, it's not as helpful for vectors. Vectors, if you're visualizing what's happening, your life is going to be a lot easier. The zero vector. The zero vector, you write with the 0 and put an arrow over top. Or as in this one, they bolded it. To travel in the zero vector, stand in one spot. and don't move. There we go. Just experience the zero vector. You're sort of doing it in your desks, all class. So if you go from P to Q, and then Q to R, and then back to R to P, right? Or we can make the zero vector kind of funny, right? If you've got your origin here and some point P, you could go back to the origin and then back to P, and that would be the zero vector. But writing it out. That's your zero vector. Yeah, it spells poop, which is kind of... Right? You guys, look at that. You guys are in grade 12. Pull out the grade 1 humor, and you just love it, right? We got 15 minutes left.
I felt like every time we finish a section.
No, we're going faster.
We're going faster so you get more time to study and less stress at the end. So we don't finish class and then be like, test is the next day.
And no test on the
That's-
last day.
And then we don't have a test on the last day. That is the plan. Okay, geometric proofs. So we are going to start figuring some stuff out geometrically that you could have used to be able to do maybe with your other formulas, but now with vectors, you have a different way of figuring them out. Okay, so we'll start off with this. You've got two position vectors m and n with respect to the origin. So you can go from m to n quite easily. M to n would be going from m to o, and then o to n. Ooh, the vector moved. Not as exciting as my last vector, but still made a word. Will just be negative m plus n. And same thing, you could write n to m as going from n to o, and then going from o to m, which would be negative n plus n. Or you could figure out n to m by just taking the negative of m to n. So now this is where the geometrical proofs start to come into play. You have a robot that can only travel along the route m and along the route n. And you have the point P, which is halfway between m and m, and you want to tell your robot to get there. How is it going to travel from O to P, but only being allowed to travel in these directions?
Excuse the interruption, a very important announcement that we're entering a hold and secure, which simply means that everybody remains in the building until further notice. We're going to have a break coming up, 15 minutes. We have our break, we move around the building as usual, but we stay in the building. The doors are just being secured right now by staff, but again, students, just stay in the building until further notice. Thank you.
So what that means is everything is normal, but I have to teach like everything is exactly the same. The only thing difference is if during your break you always went and did a run on the track outside. That is no longer allowed, right? 15 minutes, your record is 2.5 times around, and each time you try to beat it, no, you can't do that. You're only allowed to stay in the building, so you can run the A block, but there's going to be lots of people in the halls, so it could be dangerous.
Wait, until we'll be secure, can we actually will do like
In security.
but like they can tell me I can't leave.
That's right, you can't leave the building.
But what if I have stuff going on?
Then you are, they're saying they would rather you safe. Okay. So what have we found out so far? We have found out so far that we could go from M to N, right? You're allowed to travel that way. So what I'm going to tell my robot to do is I'm going to tell my robot that if I would go from O to N, O to M, and then just tell it to go halfway along N to N, I would get from O to P. Does that make sense? And so now, I go from O to M, and I go halfway from M to N, and O to M I know is my vector M. And I know that minus M plus N, I figured that out in part A, was M to N. And when I put everything together and combine my like terms, oh, this is exciting. It says half M plus half N. So I'm going to erase what I've got here. And in green, I'm going to draw, wow, start again. Half of M, and in purple, I'm going to draw half of N. Now, if I took half of M and I added half of N, look at that, it goes right to P. And this is how I would tell my robot, if you want to get to P, this is what you should do. If those are the only pathways you're allowed to travel, go halfway along M, and then change directions and go halfway along N, and you'll get to point P. So you invent a more sophisticated robot that can travel in 3 directions rather than just 2 directions. And what we're going to tell our robot to do is, in traveling only in these 3 directions, how can we go from P to Q? But it's only allowed to travel along routes A, B, and C. What we know is P is the midpoint between A and B, and Q is the midpoint between B and C. So if I wanted to get to P, I could go from O to A and go halfway from A to B. And of course, A to B is going to be minus A plus B. Add my little vector heads on there. So So we figured this out already, that P was a half of A plus a half of B. And similarly, we could figure out that O to Q would be like going from O to B and then halfway of B to C, which would be vector B and then negative B plus C. So we get half B plus half C. So now if I had my robot at point P, and I need my robot to get to point Q, I could go back along the green dotted line, which was O to P, because I figured that out already, and I could go along the dotted blue line, which is C, because I figured that already. So that would be P to O plus O to Q. And P to O is negative O to P, so I get negative 1/2 A plus, or subtract negative 1/2 B, plus 1/2 B, plus 1/2 C. And if I combine my like terms, I just end up with negative 1/2 A plus 1/2 C. So I'm going to draw this out. I'm going to draw negative 1/2 A, so half of A would go to there, negative of it would put the arrowhead on the other direction. And 1/2 of C I'm going to do in light blue. I'm going to draw it on here. There's 1/2 C. So apparently, if I start at P and move this orange one to P, that's negative 1/2 A, and then draw the blue one on there, I go from P, I end at Q. And if I was at P and wanted to get to Q in that direction, that's what I would tell my robot to do. Which is kind of cool. I really like when you get your final answer and you draw it out and then join them up and it works out. It's like, oh, that's kind of cool. And that's why vectors being free, you figure them out, but then you can move them all over the place. Example 3. The point O is at the center of a regular hexagon, ABCDEF. Could have totally used different letters and made up a word. Should have done HEXAGN. And have the O as the origin, like almost spell hexagon. But ABCDEF is this. And the only things that we know are this green vector and this blue vector. You know that O to A is A and A to B is B. How would you go from O to B? Well, if you're only allowed to travel along the green and blue lines, I would go from O to B by going from O to A, and then going from A to B. So O to B will just be A plus B. How would you go from B to D? From B to D, this is what we want to do. We want to start here and we want to end here. You could figure this out in a bunch of different ways. Okay? one, you could just go back here from B to A, back from A to O. Can you see from A to O if you, because it's a hexagon, if you kept it going, it would go to the other one. So B to D would be from B to A plus 2 AOs, which would be negative B minus 2A's. You could do this in a more complicated way as well. Check this out. I'm going to add, we already figured out O to B in purple, right? Can you see that you could start at B? If you traveled A, that would take you along that line. And then traveled the purple one and backwards, that would take you along that line. Because of the parallelness of the hexagon. So this one would be negative A. Oh, I'll do it in green. This one would be negative A. And this purple one would be negative B, which is negative bracket A plus B. And you put those together, you get negative 2A plus, negative 2A minus B as well. So the fact that vectors are free allows you to think about going from one place to another via any path that you would like. And the hexagon is nice because it has so many parallel lines. Hexagon is also nice because did you know that each one of these triangles that are made inside the hexagon are equilateral triangles with 60 degrees? So all of their lengths are the same? So if I want to go from C to F, can you see that that's just a negative B and a negative B? And you get negative 2B. All right, that's where we'll stop for today.